There is a version of this story that begins with you, with a birth, a home, a family, a name. But that is not where this story actually begins. This story begins 4.54 billion years ago, in a place with no ground to stand on, no air to breathe, and no light steady enough to call a sky. It begins as a cloud of gas and dust, cold and dark, drifting quietly in a corner of the galaxy that had no name yet, because there was no one to name it. And somewhere inside that cloud, gravity was about to do something extraordinary. It was about to build a star, and almost as an afterthought, it was about to build a planet. This is the story of that planet. This is the story of how Earth was born. To understand how Earth began, we have to start slightly earlier, with the birth of the sun itself. About 4.6 billion years ago, in our region of the Milky Way, there existed a vast, slow-drifting cloud of gas and dust called a molecular cloud, made mostly of hydrogen left over from the early universe, mixed with heavier elements forged in the cores and death explosions of earlier generations of stars. Scientists believe something disturbed this cloud, perhaps the shock wave from a nearby exploding star, causing a dense pocket within it to begin collapsing under its own gravity. As the cloud collapsed inward, it did something clouds of gas naturally do when they fall into a smaller space while spinning. It flattened. Conservation of angular momentum turned the collapsing sphere into a wide spinning disk, with almost all of the material pulled toward a dense heating core at the center. That glowing core eventually became hot and compressed enough to ignite nuclear fusion. Hydrogen atoms began fusing into helium, releasing immense energy. A star had switched on. Our sun had been born. But not all of the material fell into the sun. A thin, swirling disk of leftover gas and dust remained in orbit around it, what astronomers call the protoplanetary disk. Its age has been measured with remarkable precision using a particular kind of ancient rock. Meteorites, many of them unchanged fragments from this very early disk, contain tiny mineral grains called calcium-aluminum-rich inclusions, believed to be among the first solid materials to condense out of the cooling disk. Radiometric dating of these grains places the birth of our solar system at approximately 4.567 billion years ago. Within that thin disk of leftover dust and gas drifting quietly around our newborn sun, the raw material for every planet, including the one you are standing on right now, was already in place. It is genuinely strange to think that a planet as large and solid as Earth began its life as something closer to smoke. Within the protoplanetary disk, tiny grains of dust, some barely larger than particles of ash, began to collide with one another. Most collisions simply destroyed the particles. But some, at just the right gentle speed, caused the grains to stick together, held by weak electrostatic and molecular forces. Over time, dust grains became pebbles. Pebbles became boulders. And boulders, through a process still actively debated by planetary scientists, eventually became objects large enough for their own gravity to matter, kilometer-sized bodies called planetesimals. Once an object reaches planetesimal size, gravity itself becomes the dominant force, pulling in nearby material in a runaway process appropriately called runaway accretion. Larger bodies grow disproportionately faster than smaller ones, quickly outcompeting their neighbors. Within roughly 100,000 to a few million years, this process is thought to have produced dozens of planetary embryos scattered throughout the inner solar system. Bodies ranging from the size of our moon to the size of Mars, each one on its own unstable orbit, each one destined to collide with its neighbors. What followed was not a gentle assembly. It was a demolition derby lasting tens of millions of years. Planetary embryos crashed into one another with tremendous violence, sometimes merging, sometimes shattering, gradually consolidating the inner solar system down to the rocky planets we know today: Mercury, Venus, Earth, and Mars. Earth itself is estimated to have taken somewhere between 10 and 100 million years to fully assemble to something close to its current mass, based on isotopic evidence from short-lived radioactive elements present in the early solar system. That timescale is worth sitting with for a moment. It means that for tens of millions of years, the space where Earth now orbits was not yet a planet at all. It was a war zone of colliding worlds, glowing, cratered, half-formed bodies, smashing into one another over and over, slowly building something larger out of the wreckage each time. Out of that wreckage, one particular body kept winning. It kept growing. It kept surviving its collisions instead of being destroyed by them. That body was Earth. How do we know, with any real confidence, when this violent assembly was more or less complete? The answer comes from radiometric dating and from a very unusual archive: meteorites. Certain radioactive elements decay into other elements at fixed, extremely reliable rates, unaffected by heat, pressure, or chemical environment. By measuring the ratio of a radioactive parent element to its stable decay product within a rock, scientists can calculate how long ago that rock solidified. The difficulty with using this method on Earth itself is that Earth is geologically active. Plate tectonics, volcanism, and erosion have destroyed almost all of its oldest rock record. The very oldest known Earth rocks, found in Canada's Acasta Gneiss complex, date to about 4.03 billion years old. And the oldest known individual mineral grains, tiny zircon crystals from Western Australia, have been dated to about 4.4 billion years old. But neither tells us when Earth itself first formed, only that it already existed in some form by those dates. To find Earth's true starting point, scientists turned instead to meteorites, untouched fragments of the original protoplanetary disk, chemically frozen in time since the earliest days of the solar system. In 1956, geochemist Claire Patterson used the radioactive decay of uranium into lead, measured across several meteorite samples, to calculate an age for the solar system, and by extension for Earth, of approximately 4.55 billion years, one of the most influential measurements in the history of geology. Decades of refined analysis using multiple independent radiometric systems have since converged on a figure of 4.54 billion years, with an uncertainty of only about 1%. This is worth appreciating for a moment. Without a single fossil, without a single written record, without anyone present to witness it, scientists have determined the age of our entire planet to within roughly 50 million years, using nothing but the patient measurement of radioactive decay in rocks that fell from space. Newly assembled Earth was not the layered, structured planet we know today. It was closer to a single, roughly uniform ball of rock and metal, its ingredients mixed together in no particular order, because that is simply how accretion delivers material. But Earth did not stay that way for long. Almost immediately after its formation, it began to sort itself out, driven by heat. Early Earth was extraordinarily hot, for at least three overlapping reasons. First, the sheer violence of accretion itself converted enormous amounts of kinetic energy into heat on every impact. Second, the decay of short-lived radioactive isotopes, particularly aluminum-26, released substantial heat as the young planet's material broke down. Third, gravitational compression itself generated additional heat, simply from the weight of material pressing inward. Combined, these forces are thought to have melted a significant portion of the young Earth into a churning ocean of liquid rock and molten metal, a magma ocean likely hundreds of kilometers deep. In that molten, fluid state, something inevitable happened. Just as oil separates from water, denser materials sank while lighter materials rose. Molten iron and nickel sank steadily toward the center of the planet. Lighter silicate rock rose toward the surface. Geologists sometimes call this, dramatically but not inaccurately, the iron catastrophe, the point at which Earth's dense metallic core separated from its rocky mantle. We can measure how quickly this happened, using a radioactive clock built into the chemistry of the process itself. Hafnium, a rock-loving element, and tungsten, a metal-loving element, are normally separated from each other the moment core formation occurs. But radioactive hafnium-182 continues decaying into tungsten-182 wherever hafnium remains behind. By comparing tungsten isotope ratios in ancient rocks, scientists can determine how much time passed before Earth's core finally separated from its mantle. That evidence points to core formation happening remarkably quickly, largely complete within the first 30 million years of Earth's history. The result, still with us today, is the layered planet beneath your feet. A solid inner core and liquid outer core of iron and nickel, a thick, slowly flowing rocky mantle above it, and floating on top like a thin scum, the fragile crust, the only layer any of us has ever actually stood on. Earth, in other words, spent its first few tens of millions of years quite literally turning itself inside out. While Earth was still finishing this internal reorganization, while its core was still separating, while its surface was still an ocean of molten rock, one more collision was coming. And this one would be unlike any of the others. For centuries, the origin of Earth's moon was a genuine puzzle. Several competing ideas were seriously considered across the 20th century: that the moon spun directly off a rapidly rotating young Earth, that it formed elsewhere and was later captured by Earth's gravity, or that Earth and the moon simply formed together, side by side, like a double planet. Each ran into serious problems once tested against precise orbital and chemical evidence. In the mid-1970s, a different explanation was proposed: that the moon formed from debris created when a Mars-sized planetary body collided catastrophically with the young Earth. Scientists named this hypothetical impactor Theia, after the mythological mother of the moon goddess Selene. According to this giant impact hypothesis, sometime within Earth's first 100 million years or so, Theia, roughly the size of Mars, carrying perhaps 10% of Earth's mass, struck the young Earth at a grazing, oblique angle rather than head-on. The energy released would have been almost incomprehensible, enough to melt or vaporize a substantial portion of both bodies. A vast plume of molten and vaporized rock, drawn from Theia's outer layers and Earth's own, would have been blasted into orbit around the wounded, reforming planet. That debris did not simply fall back or drift away. Computer simulations show it would have quickly formed a hot, dense ring of orbiting material, before rapidly reaccreting through the same gravitational clumping that built the planets in the first place, into a single new body, the Moon. Modern high-resolution simulations suggest the entire sequence, impact, debris disk, and lunar accretion, may have unfolded remarkably quickly: an initial debris disk within less than a month, and a fully accreted moon within a period of months to perhaps a century. A hypothesis this dramatic demands strong evidence. And the giant impact hypothesis remains the leading scientific explanation for the moon's origin precisely because that evidence exists, gathered largely from actual samples of the moon itself. Between 1969 and 1972, the Apollo missions returned 382 kilograms of lunar rock and soil to Earth, allowing scientists to directly compare lunar chemistry to Earth's own, a comparison that produced one of the strongest lines of evidence for the hypothesis. Oxygen exists in nature as several isotopes. and their precise ratio varies slightly depending on where in the solar system a rock formed. When scientists measured the oxygen isotope ratios of lunar rocks against Earth rocks, they found the two nearly identical, far closer than ratios found in meteorites known to come from Mars or the asteroid belt. This was, in a sense, unexpected. If the Moon formed primarily from Theia, a separate body, its isotopic fingerprint should logically differ from Earth's. Instead, the Moon's chemistry looks remarkably like Earth's own mantle, a puzzle that remains an active area of research rather than a fully settled question. One leading explanation suggests the collision was energetic enough to thoroughly mix material from both bodies before the Moon formed, erasing much of Theia's original signature. Another proposes the impact was extreme enough to briefly vaporize both bodies into a huge, donut-shaped cloud of molten rock enveloping the whole Earth, a structure some scientists call a synestia, within which Earth and the forming Moon shared a common, well-mixed reservoir of material. None of this is treated by scientists as final, unquestionable proof. That is not how science works. The giant impact hypothesis is simply the model that currently explains the widest range of observed evidence, with the fewest unresolved contradictions. And it is therefore the model the overwhelming majority of planetary scientists currently favor, even as new samples and new data continue to refine its details. Whatever its precise details, the outcome of this event mattered enormously for everything that came after. The newly formed Moon in its earliest days would have orbited far closer to Earth than it does now, possibly only about 3 times Earth's own diameter away, compared to roughly 30 Earth diameters today. Seen from Earth's surface, it would have appeared many times larger in the sky than it does tonight. That proximity mattered because it meant a dramatically stronger tidal pull on the young Earth than the Moon exerts today, a detail relevant to several later chapters of the story, including the shaping of Earth's very first oceans. Over billions of years, the Moon has been slowly drifting away from Earth, at a rate still measurable today. About 3.8 centimeters per year, confirmed by laser-ranging experiments using reflectors left on the lunar surface by Apollo astronauts. The giant impact is also thought to have influenced the roughly 23.5-degree tilt of Earth's rotational axis, responsible for our seasons. And some researchers propose the Moon's gravitational presence has helped stabilize that tilt over long timescales, preventing the more chaotic wobbling some models suggest less Moon-stabilized planets like Mars may experience. So the same catastrophic collision that nearly destroyed the young Earth also left behind, in its wreckage, a companion that would go on to quietly shape the planet's climate, tides, and stability for billions of years afterward. Let us take stock of where this leaves us. In the space of perhaps 100 million years, a span almost impossible to hold in the mind, though genuinely brief by the standards of a planet's entire history, a quiet cloud of interstellar gas and dust had collapsed into a star. A thin disk of leftover material had clumped, collided, and consolidated into a small number of rocky worlds. One of those worlds had melted, turned itself inside out, inserted itself into a metallic core, a rocky mantle, and a thin outer crust. And that world had survived a collision violent enough to blast a portion of itself into orbit, where it reformed into a companion moon that would orbit it for the rest of its existence. None of this involved life. None of this involved oceans, or air fit to breathe, or a single drop of liquid water resting calmly on a stable surface. The Earth that existed at the end of this process was closer to a wound that had not yet finished healing. A scarred, molten, newly reassembled world, its surface glowing, its atmosphere thick with gases no living thing could survive. And yet this violent, chaotic, almost accidental sequence of events is the reason any of us are here at all. The iron beneath your feet right now settled into Earth's core during that early chaos. The tilt of the axis that gives you your seasons was very likely set, at least in part, by that same catastrophic impact. The Moon that quietly pulls at your ocean's tides tonight is the physical debris of that collision, still in orbit 4.5 billion years later. Earth was born a violent world, forged out of collision, heat, and catastrophe. and it was not finished yet. The bombardment was not over. The atmosphere was still poison. There was, as far as we know, still no ocean of liquid water resting calmly anywhere on its surface. That is where we go next. If you'd like to keep exploring this story with us, consider subscribing. It helps more than you'd think. Thank you for watching, and I'll see you in the next chapter.